Hello, and thank you for listening to my presentation today. This is joint work between myself, Henning Schulzrinne, and my PhD students, Jan Janak and Luo Yao. I want to make the point today that the smart city is more than a network, more than 5G, but it is about creating a flexible, heterogeneous, and programmable infrastructure. What are some of the challenges for the smart city? Smart city is clearly not just a city-scale smart homes. It combines many more sensors and actuators operated by many diverse and often conflicting sectors and administrations. It is not meant to be application-specific or vendor-specific. Thus, there are interactions everywhere. In particular, that means we need to decouple the IoT function, the sensor and the actuator, from device identities if we want to be able to reuse the same sensors and actuators for multiple functions. It is indeed an IoT ecosystem consisting of living organisms, non-living components, and all interacting by communications. There has been a lot of discussion that 5G is going to dominate the smart city communication networks. I don't think that's likely, simply because the variety of networks that we have or likely to have offer different advantages and suffer different drawbacks. For example, in some applications, the low monthly cost may argue for a Wi-Fi solution. In others, a regional but outdoor-dominated application might be better served by LoRaWAN or a narrowband IoT solution, and we are likely to have applications specific, for example, to connected vehicles or agricultural centers or remote areas. Thus, we're going to be faced with a challenge of combining many networks, many network addresses, and many network administrations across the smart city application space. Our approach suggests a directory-based mechanism. Why should we use directories as a core part of a functioning, extendable smart cities ecosystem? They allow us to manage the growth of data. They can allow us to discover not just sensors and actuators, but also time series and data stores. We can discover resources, again, not just sensors and actuators, but also transformation services. Most importantly, and the focus of this particular presentation, they allow us to hide changes that happen in a large ecosystem by providing a name resolution mechanism that is meaningful to the application and independent of the details of the hardware and vendor. They also allow us to share data, since they provide a common reference so that we do not have to be concerned as to who operates a particular device or service. We will be describing here a location-based, hierarchical, and distributed system based on such a directory, managed by a separate administration or a federation of administrations. And importantly, we need to, from the very beginning, support access control for both the directory lookups and the actual access to the service and device. The first component is geospatial naming of IoT services. Let me step back a minute and emphasize how important programmability has been for networking services in general. Nobody wants to program raw protocols, whether that's TCP or HTTP or MQTT. Indeed, one can argue that the most significant advances in making the internet usable to a wide variety of applications were not just the protocols, but also the APIs and programming services that went along with those. Starting in the early 80s with a socket API still around, the Java networking APIs, things like PHP that allows you to treat network input as script variables, and Ruby on Rails a number of years ago that simplified common network interaction patterns. On the other hand, we have plenty of examples where protocols and frameworks failed the test of programmer hate. Programmers just didn't like to create those, partially because of complexity, partially because it was hard to see what exactly was going on. For IoT, this will be even more important because most of the people programming IoT services and the smart city specialist will not really be programmers and software engineers by trade. They will be people like data scientists. And they certainly don't have a protocol background. One of the most important aspects of programs is naming. For IoT, this is even more important because inadvertently addressing the wrong device could cause significant damage in the physical world, or indeed could cause the system to cease functioning, and often silently, as in it will appear to be working but not actually perform its task. Currently, many IoT systems rely on low-level naming, often related to the network address. These don't work. IP addresses can change. NATs make IP addresses non-unique, particularly across administrative domains. Even MAC addresses can change when a hardware swap out occurs. The same device in terms of function is replaced by some other device with a different Ethernet interface. Domain names seem like a good option, and indeed in some cases they can work, but they're often unpredictable. They're often assigned automatically based on IP addresses and thus suffer from the same problem. They're assigned randomly, or they're assigned based on the manufacturer name as opposed to the actual service they provide. So what are our requirements? We want to have something that has no dependency on hardware or network topology. It needs to be independent of the administrative domain. And most importantly, the semantics of a naming should be meaningful to programmers. That, among other advantages, will likely reduce the number of errors that occur simply because it is clear to an observer of a program what the program is supposed to be doing, as opposed to guessing that this is actually doing the right thing. And we also want to have the capability for a programmer to easily address both a single device as well as a collection of devices, or have the ability to have fallback devices that automatically get drafted. So the first available device gets programmed into the functionality. So what is the kind of scale that we're talking about for smart city applications? Just as some examples, the largest number, if we were to look at energy type of applications, we're looking at about 136 million residential meters. We're looking at probably several tens of thousands of traffic lights, about 5 million parking meters, which just New York City has tens of thousands. Then we have about 270 million cars and trucks. And we have also a very large number of light posts, estimated at anywhere between 26 and 44 million in the US. They often have the advantage of being connected to fiber, so they make natural points of network attachment. So what are the concerns and advantages of geospatial IoT device naming? First, IoT device names are primarily meant for people, not for machines. So they should be meaningful to people, including programmers. We think of that as a program function and variable names in traditional programming. Indeed, for many IoT devices, think of a home automation type system, we typically refer to these physical objects by their location. We talk about the light switch in the living room. But even for smart cities, location is one of the principal distinguishing factors. We talk about the security camera at a particular intersection. Indeed, we use that as a classical reference in smart speakers, for example, where we refer to the device by its location. We don't talk about the manufacturer of a device, certainly not the network address of the device. Thus, we believe that intuitive IoT device names often have a geospatial component. It is easier for people to use and understand. That's not always the case. For some mobile applications, for example, that may not be particularly relevant, or for quite complex, let's say, manufacturing systems, function and other references may be more appropriate. But for many smart city applications, we believe that geospatial IoT naming for programming and user interfaces is the appropriate approach. To illustrate what would this look like, this is a kind of pseudo-programming model where in Pseudopython, where we would want to discover devices in a certain location of a certain type. And so we would simply enumerate those and then, say, output the concentration of carbon monoxide, say. Or we could envision an SQL-like interface, possibly even a real SQL database as the backbone, which allows us to do all the standard queries and indeed leverage the geospatial functionality that is embedded in many common SQL database systems. So if we want to map IoT devices to locations, we have some sources of that location data. Google Maps is one possibility, OpenStreetMap, building on information management systems, and just simple, good old-fashioned floor plans. They have trade-offs shown here. Generally speaking, we believe that OpenStreetMaps combined with floor plans provide the best combination, primarily at least for indoor type of smart city and building automation applications. We have been exploring a prototype to use multiple user-accessible data sources, in particular to use the OpenStreetMap building data. It provides polygons in JSON format, and then indoor plans, the fire escape plans, and similar type of readily available plans. Now, some smart cities will have more formal data available, GIS systems, so they will certainly have higher quality data in that. But for many more localized applications, relying on cheap and easily accessible data provides a quick way to get started. We have been building systems to convert this raw data to a geodatabase, essentially combining floor plans, such as the one shown here for the floor where our lab is situated, with the OpenStreetMap data so that the floor plan is appropriately aligned via reference coordinates, and then we assign names to those to be meaningful. What do we get? We get a database of JSON objects that are in WGS84 longitude-latitude format, essentially a 2.5D model, largely XY coordinates, but augmented with floor information. And then we import those into the MongoDB or Postgres databases. Again, this does not preclude use of a real JS system, but this provides a low-cost, easy to program mechanism to get a large fraction of the same result. So we then create a directory database of IoT devices, each provided with a longitude, latitude information, in addition to additional civic data, such as street addresses and room numbers and so on. And then we also provide an API that allows us to query that data. But naming devices is not sufficient. We also want to provide access control so that only authorized users can access and change the data for IoT devices. So access control, I can offer a variety of factors in making that decision. Well-known attributes-based or role-based or identity-based access controls. In multi-administrative type of settings, the biggest challenge is not defining those roles and attributes, but providing reliable sources of those that are understood and trustworthy across administrations. That remains a challenge. We can use time. So, for example, we can restrict access to certain time of day or also to certain frequencies of access. So, for example, we might restrict less privileged users to infrequent access, as that often addresses concerns about privacy or the ability of external users to either intentionally or inadvertently overload the system. However, we were focusing here on the third approach, namely using geospatial access control. That is less well understood than the other mechanisms, but because it is rooted in the physical world, we believe that it provides an intuitive access control component that can kick in when some of the others may not be as appropriate. Again, this is likely to yield an access control system that is a combination of all three, not just role and identity and attribute, but time and geospatial information. Indeed, we can imagine that access control on a university campus is a good example of that. It is typically based on time of day. It has some notion of role and identity, but in many cases, it's also based on spatial properties. So if you are in a certain place, you gain other rights. We use access control based on geospatial relationships in traditional systems all the time. The light switch is a classical example. We do not put passwords on light switches most of the time, but we simply assume that somebody who is in a room has the authority to turn the light on and off. So we provide write access if you're near a particular object, and we might only want to provide read access if you're further away, thus limiting the damage that a far-away attacker can do. We might also want to have a separate access right for discoverability independent of the access rights given to control. So, in summary, we propose that we want to use identity and role if the identity of the user is known, but we do not need identity in all cases because in many cases, simply the position of the entity, if verifiable, is sufficient to distinguish between authorized and unauthorized use. In our model, since location is not precise in most cases, but is really an uncertainty ring, we have the simple rules that if a probable location does not overlap with the authorization area or only partially overlap, we deny access. Only if the probable area fully falls within the authorized area, then we grant access. And each IoT device can independently determine what kind of a right it grants based on the size of that particular right access area. In summary, we believe that we will have a combination of many access networks for a smart city, indeed an Internet of Things. But the hard part is not the network. We understand that pretty well. The technology is likely to change over time and will likely combine a variety of network access technologies. The software is likely going to be the far larger challenges. It needs to be able to be created by domain experts. It needs to be extremely reliable and it needs to be maintainable over decades. We believe that directories can play a crucial role in hiding dangerous details that programmers should not incorporate into their programs and provide a natural means of implementing both discovery and access control. In particular, for smart city, geography is the most natural component of both naming and access control, complementing some other like function or identity-based access control. Thank you very much, and I look forward to your questions.